Okay, and I guess it's working right now. So let's start. Today, I will want to talk about partition calculus, which is one of my favorite subjects in set theory because of Was I muted? In that case, I'll just start again. Welcome, everyone. This is lecture number 10 in set theory. The main topic will be partition calculus. And but before we start, there are one or two things that I want to mention about stationary sets that I didn't mention explicitly, but you should keep those in mind when you're working with them. The first thing is that I may have mentioned this, but I want to be explicit. First thing that I may have mentioned or not, but I should have, is that the cup filter, the filter generated by the closed unbounded sets, is not ultrafilter. Well, I have mentioned that there are disjoint stationary sets, and one of the homework problems was to find even on omega 1 a family of, well, LF1 many disjoint stationary sets. Each of those could be added to the cup filter, and so the cup filter is definitely not maximal. However, there are a few interesting things that can be said about this statement. If kappa is larger than LF1, you don't need to do anything to show that the cup filter is not an ultrafilter. Why? Well, here is a stationary subset of kappa . And here is another one. These two sets are stationary in your regular cardinal bigger than LF1. And there's no effort in writing them down. You take the limit ordinals of countable cofinality, the limit ordinals of cofinality LF1. Certainly these two sets are disjoint. And it's an easy, relatively easy exercise. To show that both are stationary. Now, this is a bit unsatisfactory because why is it so easy for larger cardinals, and what is the deal with LF1? Well, LF1 is a bit of a special case. I set this aside because like I said, there is something interesting going on. If we take the axiom of choice, then as you will have seen in the homework, the cup filter is not ultra. And for example, here is a proof that doesn't rely on the homework. There is an injection from omega 1 into R, and now use, I think, one of the homework problems. To show that there is no sigma complete ultrafilter on the reals, and then no subset of the reals has a sigma complete ultrafilter either. And the cup filter is sigma complete, so there. However, in the class that was taught parallel to this course, the Capita Selecta of this year, and now you will have to find there you will find that there is a model of ZF in which I think this was our notation. In which the cup filter on LF1 on omega 1 is an ultrafilter. And this is, I'm not going to say that this is easy, but this is all part of descriptive set theory and something called the axiom of determinacy. You can look that up later. So I just wanted to point out that there is a difference between the larger cardinals, larger than LF1, and LF1 itself in this respect. There is way more interesting stuff going on LF1 than there is on the larger ones. Nevertheless, Solovey showed, and you can find the proof in Jeff's book, there is a general theorem that you can split the every stationary set of every regular cardinal into kappa many pieces, just as many as the cardinal is big. So the theorem, the proof of the theorem is not overly difficult. It relies on Fodor's pressing down lemma a lot, but it can be done in, I think, 1 hour of lecture, and it's instructive to read up on it. And the other thing that I wanted to mention, and it's just mentioned because it will come back later, we showed that the closed unbounded filter was closed under taking diagonal intersections. So if we had The diagonal intersection of any kappa sequence of closed and bounded sets was closed and bounded again. We showed that last time. Filters that have this property, if you take a kappa sequence of elements of the filter and its diagonal intersection is again a member of the filter, if that happens all the time, then you call that thing a normal filter. Now, an interesting exercise in no, it's not an exercise, it's a theorem. It says that if you have a filter that is normal, then it is finer than the cup filter. Okay, it needs one tiny technical condition, but that technical condition is usually met, so we don't really worry about it. If F is normal, then every closed and bounded set belongs to that filter, which is an interesting thing to know, but it shows you that normality and closed and bounded sets have lots in common. And it also shows you that if you have a normal filter, then all the members of the filter are stationary sets. So that's another thing. And one of the things that will interest us later when we talk about large cardinals is if we want normal ultrafilters, if we want ultrafilters that are closed under this diagonal intersection business, then we will end up in the realm of large cardinals again. So I just wanted to tell these few things about stationary sets so that they are recorded for later. And just to tell you that basically all the things that we're talking about are geared towards all those large cardinals that we'll be talking about. And here's another thing that has lots to do with large cardinals in the end, to a certain extent at least, and that is Ramsey's theorem. It's one of the nicest results in combinatorial set theory that I know, and we'll prove it and we'll reprove it. And again, we will do some things to it that will lead us again to those large cardinals that are our special topic. What does Ramsey's theorem say? Well, just for fun, I looked up the original statement of the result, and I have to, of course, I didn't have my directory ready. Here it is. I will give a better statement in a moment, but this is how Ramsey formulated it. You have an infinite class set. You have two positive integers, mu and r, and let all the subclasses of R, whichever, okay, well, it's a whole mouthful, but here is what it says. Take an infinite set. Okay, we'll just take omega. Take two positive integers. Well, I take n and k because that seems to be the tradition in Ramsey theory to call the one number n and the other k. And then we take all the R combinations of omega. So we take the n element subsets of omega, and we divide them into subsets. How many? Mu. Well, mu is going to be Rk. And instead of dividing this family into subsets, I'll represent that partition by taking a map to K, and then assuming the axiom of selections, that is the axiom of choice, but you can do with less. So for every so we are given, well, let's say omega is not really given. So let's rewrite this again. Given two numbers n and k and a function from the n element subsets of omega to k, then there must be an infinite subclass there is an infinite subset of omega such that F is constant on the n element subsets of H. And this is usually expressed in more, let's shall we say, descriptive language. Very often we call this map F a coloring. We take every n element subset and give it one of the k colors, and H is called homogeneous. Okay, homogeneous for F, of course, but that generally goes without saying. So this is the theorem of Ramsey. And I like to say that it means that there is no complete disorder in the universe. If you try to mix up the n element subsets of omega and divide them into all kinds of strange classes, then no matter how hard you try, there's going to be an infinite subset that doesn't notice any difference, that behaves such that all n element subsets behave the same. And the reason, what Ramsey wanted to do was look at definable subsets of structures. This was model theory. And Ramsey's theorem will tell you that if you have an infinite model and finitely many formulas, there's going to be an infinite set that doesn't notice the formulas. No two n element subsets behave differently in that infinite set. So Okay, this one, you can blame me for this statement. So that's one thing. That's a statement. So how do you prove this? Well, if n is equal to 1, then this is easy, because then we simply have a map from omega to k. So we have an infinite set that we split into finitely many pieces. Or as Ramsey said, the case n equals 1 is trivial. Let's move on to a higher case. Okay, I'll do the case n equal 2 separately, and then I will indicate how to modify this to get an inductive step. So we take a function from the pairs to k, and we take an ultrafilter. We talked about the ultrafilters last week, so why not use them? And okay, so let's have the F over here. Now, for A and omega, we can look at all the other points. And since we're only looking at unordered points, we look up. And this set over here is the union of these sets. For every I less than k, we look at all the b's above A such that the pair AB gets the color I. Okay, now U is an ultrafilter. Let's call this thing this set, let's call it CAI. So it depends on A and it depends on I. Since we have an ultrafilter, this is going to happen. In the characterization of ultrafilters, we had the 2 by 2, but we also had the characterization if the union of two sets is in the ultrafilter, then one of the two is in the ultrafilter. And if you apply that inductively, you will get that the ultrafilter picks one of these finitely many sets. And what do we do with this? Well, we do the following. We build a sequence. A0 is just 0. And A1 is just the minimum of the C of A0 and its corresponding I. And what is A2? Well, we take the intersection of both the set for A0 and the set for A1. And well, you can see where this is going. Okay, so we need only key is given, so it's already fixed. We can take the intersection of these things. This is always a member of U because U is a filter. So this is always an infinite set, and we get an increasing sequence and this is important. This is important. The function value at AL and AM is just the I that goes with AL. So, and AM can be arbitrary. All the later points in the sequence, when you look at the function value of AL and any later point in the sequence, the function value is always going to be this. And that's the whole point of this construction. We want to reduce the problem to the first case. We did it once, basically by choosing the sets C, and we're going to do it again by looking at the A's. Because the sequence of A's is infinite. We have infinitely many A's, but we have only finitely many possibilities for the IAL. So we can take an I less than K such that what? Where is it? Okay, we could say we let you do the choosing. Why not? But anyway, this set is infinite. And now we let H be the ALs, where L runs through A. And what do we get? We get that we get that when we look at L and M in I, then the function value FALAM is always equal to the little I. And so yes, H is infinite and homogeneous. Now, before I go on and look at the higher dimensional case, I want to make a few comments about this particular case, n equals 2. N equals 2 is been the case n equals 2 is special in the sense that for many people, the case n equals 2 means that you talk about graphs. Well, graphs are points and lines in between. And so the case n equals 2 this says that if you color the lines in the complete graph if we just take the natural numbers as points in the graph, we look at the complete graph on those points, so all the lines between all the natural numbers, and we color those things with finitely many colors, then there is an infinite set H. Okay, I couldn't just fit it on the piece of paper, such that all lines between members of H have the same color. And this is also where the word homogeneous often comes in. It comes actually from this graph theoretical interpretation. There is also, before I continue, there is also a finite version of Ramsey's theorem, and I want to put that here. Just to say a few more things about this this graph thing. Now the infinite class gamma is gone, and we have a natural number here. If we take 3 natural numbers and we divide, then we can find a big number m, such that the things that are going to happen are represented in the stated in this theorem. I will tell you what it means in terms of graphs given two numbers. No, let's say shall we say K. There is a number such that whenever, say, m is bigger than or equal to n, so my big N is the M0 in Theorem B of Ramsey, and the complete, if you take the graph on m points and you color the edges, the lines, with two colors, red and blue, say, then there is a subset of k points such that all lines between those have the same color. And there is a very elementary case of this that I'll mention in a moment. Now, this is how Ramsey stated it, and you can prove this in two ways. There's a really fancy proof. Compactness, for those who know what this means, of course, but you say, suppose not, and then you take a sequence of counterexamples, and then that sequence of counterexamples will converge to a counterexample against Ramsey's theorem, which is impossible. So there must be an n for which things go wrong. The problem is no information about n. A bit of more hard work. There is a whole industry in trying to determine what the best number is. And for this particular case, we know we don't know the exact numbers, but we have a decent bound for the n. So the best n is less than or equal to this number for this special case. And in a few special cases, we know exactly what we want, what we need. If you take I'm missing one, yep. If you take 5 points, then I can color the lines in the complete graph of 5 points with two colors. I just did it. And there is no homogeneous triangle. No triangle has all sides of the same color. But, and I'm not going to prove this, you should do this yourself. If you take 6 points, no matter how you try and start to color the 6 lines, but um, how many lines are there? Well, the lines between those 6 points, ultimately you will be forced to make a triangle that all edges are the same color. Could be red, could be blue, but there's always going to be one. And for those who like their games and like to see what more you can do with this, there is a game called Sim. It has its own Wikipedia page, and Ramsey's theorem says that there are no draws in the game Sim, so there should always be a winner. And that's one application of the finite Ramsey theorem. Okay, so the language, this has many applications in graph theory, by the way, this special case n equals 2. So now let's go to the higher dimensional case, and we just do the same thing. So now we try and finish the proof, and then we'll have a break. We'll go on with the other stuff after that. So we have our function. We have our function. We take an ultrafilter again. And we do basically the same trick as a few moments ago, but with a little bit more thought. So if X is a member of omega n, this wasn't really visible in the step for n equals 2, but what we really did was we took a one element subset of omega, and we look at, shall we say, AX, those are all the B's. That are bigger than the maximum of our X. And just like in the previous case, but it wasn't as much visible, we have a function we can define a function on AX. How? Well, we take a B, we add it to X, then we have an n plus 1 element subset, and we look at the color. Again, we get and there's no prizes for guessing what this is going to be. This is all the B's in AX for which the f of X union B is equal to IX. So the function f splits the set AX into finitely many pieces. Oh, by the way, AX is co-finite, therefore AX belongs to the ultrafilter U. And we have split AX into finitely many pieces. One of the pieces belongs to U. Okay, but this gives us And we're going to use this function in a moment, but I just want to emphasize that just like in the previous case where I said we reduce it to smaller ends, this is one part of the reduction. We get a function on the n element sets that sort of tells us what the real preference of those n element subsets is. But before we do that, we have to build our sequences of A's again. And we start with AI is just I. I don't know if I is really a fortunate choice. So let's. So we start rather arbitrarily, you would think. We take AJ equal to BJ as long as J is less than 1. How do we choose AN? Well, right, X is just N, by the way, but never mind. It's an N element subset of omega. It's an N element subset of omega. Oh, we can take AN to be the minimum of the set determined by this N element subset and its preferred index. And if M is bigger than N, then we also do the same trick as a few moments ago. We have our AJs. We simply take the intersection of all the special AXIXs, where X is an N element subset of this. Well, there is only finitely many of those. So there, this set belongs to you still. So it's infinite, and we can take AM to be the minimum of this intersection. All righty. And now what? Well, we apply the inductive assumption to G and the set of A's. We get this. We get an infinite set on which G, which is homogeneous for G. Oh, but now why is that the case? Well, f of x let's look at the first n+1 elements, and so here is an n element subset, and I already put them in order. So this is the smallest one, the one after that, and so on. So here we have the n-1st element, and what our whole construction says that f of x is the g of the whole point of this exercise is to reduce the problem to n element sets. And how did we do that? Well, if you look at the set of A's that we discussed, then the function value of f on an n+1 element subset depends only on the first n elements of that set. If you have two n element subsets with the same first n elements, then their function values are the same. And a set like that is called pre-homogeneous. And if you can extract a sort of homogeneous set from the pre-homogeneous set, then you're done. So our set here is the required homogeneous subset of omega homogeneous for F. Well, it's 10 to 3. Let's have 10 minutes break. I'll get my fresh cup of tea and I'll try and pause the recording for a moment, and then the next hour will continue. Okay, let's continue with our investigation into Ramsey's theorem, and also, again, foreshadowing the large cardinal business. If you look at the proof for the case n equal 2, remember that I used this ultrafilter to choose all kinds of sets and all, and we had a decreasing sequence of sets, and we had, okay, the C's had different indices, but what the important point was that we had a decreasing sequence of sets. We could actually simply, I could have written them like so. And all these were in, these were all in the ultrafilter U. So, well, that's something. And we could have gotten H in U if we could have gotten the set of A's in U, because all we did at the end was split this set into finitely many pieces and take one that was infinite, or I took one where this set of indices was in U, but that was not what we would want. We want the set of A's to be in U. If we can get this, then yes, because we simply take a member of U that is this pre-homogeneous thing, and then we would be done. But the proof offers no guarantee whatsoever. Okay. So can we get this in, can we find a more clever proof that will give us a member of the ultrafilter actually that is homogeneous? That would be nice. Well, the answer is probably not. But only, well, probably not is not quite the correct statement. What I will mean will become clear in a moment. What I'm going to show in this hour is that remember when we were talking about ultrafilters, I said that we call them Ramsey or selective. And well, the selective was easy because we knew that the selective ultrafilter could be very picky if we gave it a partition of omega. Either it picked one element of the partition or it tried to stay away as far as possible from the individual members by just taking at most one member of each. But it wasn't quite clear why they would be called Ramsey ultrafilters. But now, of course, you can get an idea. It simply says that if okay, U is our selective ultrafilter. And this is why selective ultrafilters are also called Ramsey. So you might want to phrase this as selective ultrafilters have the Ramsey property. By the way, this is if and only if. If an ultrafilter has the Ramsey property, then it is selective because why? Well, we had this characterization by using functions from omega to omega. And so what do we need? We need a member of the ultrafilter on which the function is constant or injective. Well, let us take a function from the pairs in omega to 2. Here is a coloring of the complete graph on the natural numbers. I color them 0 if if the 2 points have the same value under f, and I color them 1 if the values are distinct. And if you have a homogeneous set for this thing, then the function little f is constant on that set or injective. Okay, so this tells you that an ultrafilter with the Ramsey property is selective. Okay, well, that's good to know. But now we're going to go the other way. And for that, we need a lemma. And the lemma is more work than the rest. Once we have the lemma, we can almost copy the proof of last time and get what we want. Except I will not be copying that proof. I'll be using a slightly different proof, all to give you something to do using the group interaction. The lemma is this. And it looks a lot like what I asked a few moments ago. Can we get the sequence of A's in the ultrafilter, or the set of A's in the ultrafilter? And this is something that is close enough to that. Okay, here is the thing. We have a selective ultrafilter, and we have a decreasing sequence of elements of the ultrafilter, which is much like the case we were in when we're doing the inductive steps in the case n equal 2 for Ramsey's theorem. The claim is then okay, let's think about this for a moment. We can find a sequence of natural numbers, increasing, most likely, such that what? Well, the set of points in the sequence, the range of the sequence, is a member of the ultrafilter. That's one thing. Okay, x0 is in x0. That's not overly important, but it's nice to know. The meat of the thing is that if you look at the next term of the sequence, then it belongs to the set whose index is the previous term in the sequence. So if, I don't know, the xn's were, say, the sequence of all the primes, then the primes would point to just a subsequence of the x's, and we would want at least to every time to be the next prime in the set indicated by the prime at this point. And what you will see is that this doesn't really go very well when the sets, the x's are relatively thin. For example, if all the differences are infinite, it's going to be very hard to do this, say, with the prime numbers, for example. But anyway, it can be done, and you really, really need selectivity for that. So how do we do this? This is going to be most of the work this hour. Once we have it, we can do basically what we did a few moments ago. And let's just look at, can we get H in U? Okay, we had the C's. Those are going to, this is going to be sort of our x's. This is going to be x0, this is going to be x1, this is going to be xm, and so on. And what we did in our proof was we constructed the A's together with the C's. And what the lemma says, okay, once you have the C's, forget about the A's, we're going to make a new sequence of A's, the X's, and they are going to be the ones that give us the homogeneous set. Okay, so let's see, how is this going to work? Okay, we have a partition of omega. We have a partition of omega into these pieces. What do we know? Well, we know that this is a rather bad partition from the point of view of O, because very many things of it are not in U. Because U is an ultrafilter, X1 is in U, so the complement of X1 is not. And X0 minus XU is a subset of that. So they're not in U, so we don't really have to worry about them. So two things could happen. It could happen that the intersection of all the x's is in U. So it's an infinite set, and it belongs to U. Now, this is highly unlikely unless we already took a member of U and created the x0s around it. In this case, we just take an enumeration of the intersection. It's a member of U, so it's infinite, so there is one, and check that this works. So the other case is that the intersection is not in U. And so then no member of the partition is in U, and we can basically forget about the intersection. Because we have its complement belongs to U, and we take we apply the definition of selectivity and take a member of Y that intersects every one of those members of the partition and at most one point. And we just wanted to stay away from the intersection of the xn's. We just don't want to have anything to do with it. We basically can pretend that the intersection of the xn's is empty. Okay. So here we go. We're going to try to make the sequence of the x's, and we're going to try and make one. It's not going to work right away, but we'll see. And it's actually just a tool on the way to creating the x's. We define a sequence in Y. How do we do that? Well, okay, just look at this for a moment. Y Y intersects every one of those complements. Let's go back to the where was our sequence? Yeah, let's look at our sequence here, and let's look at our partition here. Y intersects every one of those sets in at most one point. So what does that mean? Well, it means that, for example, there are 3 points of Y that are not in X2, at most. If Y has no point here, no point here, no point here, then all the points of Y are in X2. Remember that. So at most 1 point is not in X0, at most 2 points not in X1, at most 3 points not in X2, at most 1,000 points not in X99, and so on. That means that there is only finitely many points of Y that I have to throw away, and then forever we're going to be in X0. Next step. The next step is we're going to work towards the property of the axis that we want. We're going to take the first member such that will tell us from that point on, we are sitting in the x of y0. And of course, now you can see where this is going. So we're taking all the members of y that are bigger than yn, and we want them to be so large that the tail starting at the yn is inside the x of yn. And this looks like something that's going to happen. That looks like what the behavior of the axis. Okay, but we're not quite there. We need to do a little bit more work. We're going to divide y into intervals. And how do we do that? Well, this, by the way, is a trick that is being used lots of times in this type of combinatorics about ultrafilters on omega. You divide sets into intervals and use the functions that count those things and make choices depending on those intervals, and they will usually give you what you want. Remember, y was a member of U. U is selective. I have a partition of omega. The partition is in these proper intervals. And so there is well, I should check my spelling. Okay, this is the only case that I want to have exactly 1 point in every one of those sets, hoping that it is also, well, all the things are not empty because the y's are in y. Every one of those intersections is not empty, so there is at least 1 point of y in every interval. And for bookkeeping purposes, I really want to hit every one of those intervals once. That's no problem. I can find a set that hits every interval in at most 1 point, and I can make it slightly bigger and still stay, of course, in the ultrafilter and hit every one of those intervals in 1 point. So I get I enumerate my Z in increasing order. And you can see where this is, what is going to happen. Z0 is in the first interval, Z1 is in the next interval, Z2 is in the next interval after that. So we have this behavior here. Okay, why not stick another Zn in here as well. This is the typical situation that we meet when we look at the set Z and the set Y. Okay. Okay, I think okay, don't worry, nothing really changes, but I just see that I messed up with my preparations and I don't want to start to confuse you too much. I want to re-index the numbers Z. Let's see, Z1, yes. And so here, we have this situation. And of course, here we have Zn plus 2. Okay, nothing really changes except I didn't want to confuse myself with the notation here. Because my preparations expected something else. Okay, now here we have a whole sequence of inequalities. But remember the choice of the y's. The z of n, z sub n plus 2 is bigger than y of n plus 2. So Zn plus 2 is in the Z of Yn. Really? Yes. Because Zn plus 1 is bigger than the Z of Yn plus 1. So I'll put something in between. Zn plus 2 is bigger than Yn plus 2, and that means that it is in the set indicated by the index Yn plus 1, and Zn plus 1 is less than or equal to Yn plus 1. So it means that Zn plus 2 is in Y of Zn. Okay, well, lovely. I'll repeat that. Look very closely. This is what we want. Almost. We wanted plus 1 and n plus 1. What we're getting is n and n plus 2. Well, no big deal. Either either one of these two sets is in U, not both. And they do what we want. We renumber them as X something, and we get, say, this one. So we just split the set Z into two pieces, and one of the two pieces will do what we want. Okay, that is what this is what the lemma will give us, and now we will use the lemma to prove that selective ultrafilters have this Ramsey property. And why do we want this so much? Well, in the theory of measurable cardinals, the ultrafilters that we'll be talking about there will be selective and will have this Ramsey property as well. But remember, selective ultrafilters exist under continuum hypothesis, but it's also consistent that they don't exist. So we cannot use selective ultrafilters to actually prove Ramsey's theorem. Although some people might disagree in this, but they know too much forcing for their own good. So now we're going to prove that selective implies the Ramsey property. So how do we do this? Okay. So we want to show that for every n, for every k, whenever we have a function from the n element subsets of omega to k, there is a member of the ultrafilter that is homogeneous for the function. So induction on n. Induction on n is clear. We have an ultrafilter. We don't need selectivity. That's fine. But already for n equal 2, we need the selectivity, as you have seen, because there the Ramsey property already gives us selectivity. So here we go. Let f be given. And we're going to do roughly the same thing as before, slightly differently, but never mind. We do it slightly differently from the previous proof. Now we're going to fix the natural numbers m, and we're going to color the n element subsets of its complement and see what we can do with those. Well, we can apply our inductive assumption. And we can find a set that is homogeneous for Fm. So if we take any n element subset of Hn, add m to it, then we always get the same value. Do we need to know what the value is? Yeah, okay, why not? Value Im. Okay. We can assume that the sequence is decreasing because there is no harm in making any h a bit smaller. It will simply stay homogeneous, and we just replace hm by, we just redefine the sequence so that hm becomes the intersection of all the h's that came before and the old hm. Okay, we have our sequence of h's. We take our thing as in the lemma, corresponding to the h's, of course. So we know that we have an element of the ultrafilter, and we have that x0 is in h0, and we have this diagonalization property. Okay. Now take an n element subset of what? Of the axis. Say m is the minimum of k. Then if we take an m+1 element subset of omega, or of the axis, because I'm using the indices here, we take n+1 natural numbers, take the corresponding axis, and the minimum of the set we call m, then all those later elements of k are sitting inside this set over here. And what does that tell us? It tells us that the function value of the n+1 element set depends only on the first element. Again, so we have this type of pre-homogeneity, but stronger than in our first proof. In our first proof, this value would depend on the first n elements, and in this case, the value depends only on the first one element, so to speak. Okay, now we have finitely many pieces in this. we partition the x's into finitely many pieces, depending on the value of the I. So we find this bunch of indices I such that the corresponding x's belong to the ultrafilter, and all the IXMs are the same. And then H is homogeneous. And in U. And so there. So the if we have a selective ultrafilter, then we can actually show that it has this Ramsey property, and it does what we would have liked to have happened during the proof of Ramsey's theorem in the beginning. But I should also mention that it only works, apparently, if your ultrafilter is selective to begin with. So this strong version of Ramsey's theorem, where you can get something in your ultrafilter, only works under the continuum hypothesis, for example. And it only works if your ultrafilter is selective. Now, in the next hour, I'm going to be talking about generalizations of this theorem, because so far we've been talking about countable sets. And of course, everybody, I understand, is dying to know what is happening with uncountable sets. Before we do that, I want to introduce a little bit of notation. And once I've done that, you can think about the notation, and we'll talk about the rest of the stuff after the break. But what we have shown can be written very compactly as follows. Here we have four cardinals, kappa, lambda, nu, and mu. And we say kappa arrows at least I always pronounce it so that the nu comes for the mu, which is not very alphabetical, but okay. This is how you pronounce it. It means what you will expect it to mean if or at least I hope you will expect it to mean, but after this is what it means. If you take a coloring, okay, it's a function, but in this context, everybody talks about colorings. Then there is an H in F is constant on H mu. And so Ramsey's theorem Ramsey's theorem can now be formulated very compactly by saying that LF0 arrows LF0 and K. This notation can be generalized to all kinds of other situations, but let me also note that five doesn't arrow 3, 2, 2. That is what the picture a few pages ago showed. And what I gave you as an exercise is that if you try to do that with 6 points, you're always going to get a homogeneous triangle. And so the finite case can also be expressed in this notation. And if I'm not mistaken, what I mentioned this bound that I mentioned can also be expressed in this way. If you take the binomial coefficient 2n minus 2 over n minus 1, then it arrows n to 2. Okay, this is in the finite case. We'll talk about this problem for uncountable sets in a moment. We'll have 10 minutes break. And let me try and suspend the recording. Oh, yes, it's running. And we're off. Okay, so now we have the notation. We have Ramsey's theorem. Here it is, formulated quite compactly. What else can we expect to be true? Now, this gives rise to all kinds of interesting and lovely mathematics. You might wonder, and why not? What happens if we replace LF0 by LF1? Why not? Well, not going to happen. And now you ask yourself, really, why? Well, let me put a picture up. Yeah. It's not a picture. It's, okay, this doesn't look too good. It's from a paper by Sierpinski, (1933), and if your French is as good as mine, you'll easily read that it says here that the answer is no to our question. It tells you that if you have, that there is a relation on Aleph1 such that if you want a homogeneous set, then the homogeneous set has to be countable. Only countable homogeneous sets. And how did Sierpinski do that? Well, he did it by taking an injection from omega 1 into R. And he said, well, the relation between the symmetric relation between the two, between the points is this. So he didn't formulate it in terms of graphs. He didn't formulate it in terms of partitions. But what he said is, we have a binary relation on omega 1 that's just a subset of the pairs of omega 1. So R inside omega 1 cross omega 1 symmetric corresponds to a subset of the pairs, and a subset of the pairs is a function from 0 to, from the pairs to 0, 1. 0 if you're in the set, 1 if you're 0 if you're not in the set, 1 if you are, characteristic function. So you can formulate this in all kinds of ways. And when we're 2 points in the relation, well, you take an injection. Oh, did I say that it was injective? Well, it is. It should be injective from omega 1 into the reals. And then you look at two ordinals, x and y. If x is a member of y and x is less, and f of x is an element of f of y, then the pair xy and the pair yx, of course, is in the relation. And if the thing is not order-preserving for the two, then we give them the color 0, so to speak. And then Sierpinski proved that there is no uncountable homogeneous set. Now, the interesting thing is that Sierpinski asked a question that, okay, I should say that the question that he answered wasn't his own, it was due to Knaster. But he said, what happens if I take the set that I'm working on, not of cardinality L of 1, but of cardinality L of 2? And he wrote, well, I don't know. But, and this is interesting, it is after Ramsey, but he doesn't give any reference as far as I could tell, but I'll have to look that up later. But in the paper, he has this. And this is Ramsey's theorem for the case n equal 2. And two colors, 0, 1. And he gives a proof of that just works for arbitrary many colors as well. But it's quite interesting that somebody was thinking about this kind of thing also. Actually, to get back to this question of whether the problem of Knaster has a solution if we take L of 2 as the cardinal normal to start with. So you might want to say that Sierpinski asked, whether L of 2 arrows LF1 to 2. And that is an interesting question, because Sierpinski's method, even though he didn't realize this, he actually showed that this happens. Oops, I don't need those parentheses. The example that Sierpinski gave actually shows that you can have a relation on the reals with the property that every homogeneous set is countable. Okay. So the question here, if the continuum hypothesis is false, we get a no 2 star. In a moment, I'll prove a theorem by Erdős-Rado that will tell you, yes, 2 star. So if I were to ask you, is this provable, or, is this true or false? You could say, well, I don't know. If I can say, is this true or false? You can say definitely false. If I put an LF1 here, definitely false. If I put a 2 there or a 3, probably, well, undecided. So that's, before we know it, we have started to ask innocent sounding questions. And before you know it, we're in the undecidability region. So just like that. There are a few other things that are false. And these will be, you will meet these in the homework. In general, if you take 2 to the kappa and you try to arrow kappa plus 2, 2, not going to work. So that's the general case of the Sierpinski example. Here's another thing. You could say, well, I mean, there is no real limit on the number of colors that you can use. So what happens if I take kappa many colors? Well, then you can take a graph on 2 to the kappa many points, color it with kappa many colors. You take the full complete graph, color it with kappa many colors, and there is no homogeneous triangle. And the example is not too difficult, as you will see in the homework. For kappa is LF0, you can make nice examples of these on the real line. That's also nice to know. And another thing, you can basically forget about the exponent here being infinite. You're not going to get anything sensible there. No matter what cardinal kappa you take, you can split its countable sets into 2 families such that no countably infinite set has all its subsets in one of the 2 families. That example is slightly more difficult, but not out of reach of you. And I might even put that in the homework as well. So what can we get? Well, we can get this. This is from a paper 1942 by Erdős, and it contains the theorem that we now call the Erdős-Rado theorem. but this particular case was already proven by Erdős somewhat earlier. If you have two infinite cardinals such that B is bigger than, well, a to the A, so that means 2 to the A, and we split the complete graph of power B into a sum of subgraphs, at least one of them contains a complete graph of power A. What does that mean? It means that if I take, and of course we use our own letters for the cardinals, our our B is simply the successor of kappa to the kappa, and our A is just kappa. And what does it say? If we split the complete graph into kappa many subgraphs, then one of them contains a complete subgraph of power bigger than A, so at least cardinality kappa plus. And remember, kappa plus is the cardinal successor of kappa. This is the Erdős-Rado theorem. It has a more general form where you build a tower of 2's and you can raise this exponent 2 here. But you can find that in Jack's book. I'm not going to talk too much about that. Maybe later, and if necessary, I'll indicate what the proof is, but this proof of the Erdős-Rado theorem will take the rest of this hour. Okay, so how do we do that? I know of 3 proofs of this. You can prove it using trees. You can do it like Ramsey's theorem. And what do I mean by like Ramsey's theorem? Well, where you use these sort of pre-homogeneous sets and you make sure that the color depends only on the first element of the first n many elements. And that is the proof that we're going to be talking about. But I also know of an elementary version of this proof. And before everybody starts clamoring, why don't you do the elementary version? This is a slight play on words. This uses model theory. And the Leeuwenheim-Skolem theorem. And it's only elementary in the sense that it uses elementary substructures, submodels of models. So it's not really that elementary in the sense that it's easy to follow or anything. Well, it's easy to follow if you know your model theory, but I'm going to do the second proof, and those who know their model theory will be able to translate this into an elementarity proof really easy. Okay, here we go. We put it's going to take a while, I think. Let's see. Okay, a couple of pages in my notebook. And F so we have a coloring or a splitting of the complete graph, as Erdős said it. And we're going to look for our homogeneous set of size kappa plus. How on earth are we going to do that? Well, look at lambda, which is an ordinal, and it kind of looks like this. Somewhere here we have kappa. Somewhere here we have kappa plus, and nearby we have 2 to the kappa. They might be the same if the generalized continuum hypothesis holds, or not. But this is the thing that we're going to be concentrating on. And here is the big gulf between 2 to the kappa and its successor. And we're going to build a sequence of ordinals increasing of length kappa plus that is never, ever, ever going to reach all the way up to lambda, because lambda is a regular cardinal and the cofinality is 2 to the kappa plus. And whatever we'll be doing is too small to ever reach lambda. So whatever we're doing, it's going to stop way before lambda. I will guarantee you that. And what are we going to do? Well, we're going to build a sequence. And what did I call this? We're going to take a sequence that is kappa plus long. We could also say kappa long and do the supremum at the end. Like I already mentioned, delta 0 is 2 to the kappa. Alpha limit, so that includes kappa plus. And if we have a limit, we take the supremum. The sequence is going to be strictly increasing. Okay. And notice that delta alpha is always less than lambda plus, because all the things we're talking about are smaller than lambda. Kappa plus is way smaller than lambda. So this is never going to have lambda as its supremum. Okay, successor stage. How are we going to handle that? Okay, and here is where the meat of the proof is. Once we have this, we are basically home. We can do what we did in the proof of Ramsey's theorem and get this sort of pre-homogeneous set. How do we do the successor step? Well, okay, so here's what we'll do. We stop the proof and we introduce a few things, and then later we'll pick up the proof once we've done this. Now, what do we have? We have this thing that we used in the proofs of Ramsey's theorem as well. For every eta, we have this function that works on the complement of the point eta and goes to kappa, and it has these values. We've done this a few times before. And we actually only need the ordinals below eta in our case, because we're looking at pairs, and every pair occurs in one of these functions, and we just look at the minimum maximum to decide where it goes. Okay, Now, these functions, they do something for us. That is the following thing. If x is a subset of lambda of cardinality at most kappa, if f is a function from x to kappa, then what? There may be, or not, but what we will see is that it's going to happen quite a lot of times, an eta such that x is a subset of eta and f is the restriction of the f eta to the set x. Here is sort of the picture that I have in mind. We have the set x, which happens to be a subset of some eta. We look at what f eta does. We look at what f does. And if f and f eta are the same thing on x, then we're happy. And if not, then we're not so happy, but we don't really care, actually. There may or may not be an eta such that this happens. And here is the sort of crucial definition for the rest of our if there is one eta, then there is a first one, and the first one we will call eta xf. The point of this whole exercise is that we're going to try and predict what f is going to do. And for many sets, we want to know and try and see whether f acts on our x in that way. If there is no eta, we don't really care, so we set eta x of f equal to 0. That is our, that is a function, well defined. It's defined on all the pairs xf, where x is a subset of lambda of cardinality at most kappa, and f is a function from x to kappa, which is going to try and predict that coloring. Okay, now what? Okay, we go back. We go back to our proof. There is no, I thought I said we're going to have a lemma, but that's not the kind of thing. We introduce a piece of notation, and then we go on with our proof again. What do we know? Well, we know, whoops, that's a bit. That delta alpha has cardinality 2 to the kappa, because delta alpha is less than lambda and it's bigger than or equal to 2 to the kappa. So its cardinality is 2 to the kappa. So we know that there are at most 2 to the kappa many subsets of delta alpha of cardinality at most kappa. And every one of those sets if I have a set of cardinality kappa or less, then it has at most 2 to the kappa many functions to kappa. So what does it mean? Well, if we look at all the pairs if we look at all the pairs that we have, X, F, X a subset of delta A, and so on, how many do we have? 2 to the kappa. That is what our cardinal arithmetic tells us. Okay, what do we do? Well, we let we look at all those pairs, we calculate all their etas, we collect all the etas, and we take an upper bound for those etas and add 1 just to make sure that we will be bigger than delta alpha. Delta alpha plus 1 is a supremum plus 1 of 2 to the kappa many points. So delta alpha plus 1 is definitely less than lambda. And we continue. So what's the, this completes the construction of the sequence. So now look at we said we would take the supremum of all the deltas and call it delta kappa plus. So we did. Now here it is. This, by the way, is what we usually call a closing off argument. Why? Well, suppose you have a subset of delta that is of cardinality at most kappa, and we have a function from x to kappa. That is one of the pairs that we were, well, it's a pair of the type that we were worrying about in the aside. Well, there is cofinality of kappa plus is kappa plus, and we have kappa many ordinals less than kappa plus. Every member of X is in a delta alpha. We have kappa many delta alphas. The supremum of that is less than kappa plus. So our X sits inside a delta alpha. Oh, yes, but then the eta of x and f sits inside delta. And this is what I mean by closing off argument. Delta is closed under this eta function. Okay, it's not really delta, that is, but okay, you get the idea of what I mean. Whenever I have a pair where the domain is a subset of delta and it's small, then the corresponding eta is also less than delta. Okay, why did I do this? Well, because of the following. Remember, we are still looking for this pre-homogeneous set, and here it comes. We built I don't know. We're going to build a sequence below delta. And how are we going to do that? Well, we start off easy. We take beta 0 to be 0. Given suppose we have an initial segment of our sequence to be, we do what? Well, we let X be this set. Well, this is an element of the subset. This is a subset of delta that's of cardinality at most kappa. And F is going to be F delta restricted to X. Now, and this is, people who know the Ramsey theorem now say, oh, yes, of course, this is what's going to happen. Because now we are in the situation that let's go back to our aside. Eta x of f is the first eta with the property that we have over here. Here it is. If there is one, we take the first. If there isn't one, we take 0. But delta, oops, this went too fast. Now I lost my pages, but we'll get there. Yeah, delta it satisfies this requirement. There is an eta for this pair, namely delta, but so the eta that goes with this pair is apparently smaller than delta. It is smaller than delta by our choice. So since there is one, since delta says there is an eta, that eta exists, the smallest eta exists, and the smallest eta has to be less than delta. This is, for those who are going to do model theory, this is typical for applications of the Ramsey method. Okay, let's call that oops. That becomes beta gamma. And what's the consequence of this? If alpha is less than gamma, then F beta alpha beta gamma is F beta alpha comma delta, because this is the F beta gamma of beta alpha, and this is and they are the same because they're both equal. That's what we chose the beta gamma to do. Okay, and let's put some light here. And now we're basically done. This becomes our beta gamma, and remember this. Okay, we have this construction can keep going for kappa plus many points. It cannot go on any longer because it can go longer, but we cannot use the method. Because as soon as we reach kappa plus, we cannot use our etas anymore. We would have to make other choices, but we just don't. And notice that all the betas are less than delta, so the supremum of the betas could be delta or smaller. We don't know. Okay. Just a few more lines and then we're almost done. Let I subset of kappa plus be of cardinality kappa plus such that because f delta gives us a function from kappa plus to kappa, and by cofinality considerations, that function must be constant on a set of size kappa plus. It must even be constant on a stationary set, but we don't really need any of that. But stationarity is not our main concern here. It's just cardinality kappa plus on which it is constant. And now, say with value what shall we do? Why not value chi for chrome color? Now we know that for any two elements of kappa plus, when we look at the corresponding betas, then we get the same color all the time, the color chi. Okay, that's the end of the proof, because apparently okay, the set of betas is homogeneous, and even when we add the delta to it. And it is homogeneous of cardinality kappa. Okay, that's it. I just want to make one additional remark. In the partition calculus symbol, you can also put ordinals. Why not? And you can demand that you have homogeneous sets of certain order types. If you don't look at delta, we have, of course, if we have a set that is homogeneous of cardinality kappa plus, we have a set of order type kappa plus. Just use the initial segment. Our proof doesn't give anything more except, okay, it gives order type kappa plus plus 1. And suppose you would want order type kappa plus plus 2, you'd have to work way harder for that than we did today, for example. And I'll close with one little bit from Erdős' paper. He has an example for the triangles, but it's only the triangles on the set of size, on a set of size continuum. And of course, there is an error in there. You need larger than or equal here, but you can give it a try. See if you can show that this is a partition where you don't have any homogeneous triangles. That paper of Erdős of 1942 is completely in the language of graphs, by the way. It's all about pairs and everything. Okay, that's it. Next week, we'll have one more partition theorem, and we're going to be looking at trees. Now I need to stop.